We know that the change in enthalpy at constant pressure for a system is equal to the heat gained by the system. That's how we're planning on calculating these delta H quantities for our chemical reactions, by measuring the heat. But how do we measure that heat? Well, that's the subject of calorimetry, and you can read about it in section 5 of chapter 5. So calorimetry, literally the word calor means heat, imetry means the measurement of something, is the measurement of heat. We can determine the heat by literally measuring a change in temperature with a thermometer, and by knowing the heat capacity of a substance. The heat capacity is a measure for each different substance of how much heat it can store at a given temperature, in some sense. Now, we're going to have 3 different types of heat capacities that we will use, and you need to pay attention to the units, because the units will be different, and we'll be setting up problems slightly differently depending on the units on the heat capacity used. The first type of heat capacity I want to talk about is the heat capacity of an object. All right, by an object I mean some sort of composite thing. It's not a pure substance. And this is usually denoted with a capital C, and it's just the amount of heat required to raise the temperature of the object by 1 degree Celsius. Again, this is almost exclusively used for things like calorimeters as instruments. Calorimeters have many different parts made of different substances, and rather than try to take the heat capacity of each substance and combine them somehow, we just say, oh, heck with it, it's one big object. How much heat does it take to warm the whole thing up? That's the heat capacity of an object. If, on the other hand, we have pure substances, then we can either refer to the molar heat capacity, and it will always be labeled molar, and it's denoted with a capital C with a subscript m. It could be a lowercase m in this case. It's the amount of heat required to raise the temperature of 1 mole of substance by 1 degree. So a molar heat capacity would have units of joules for the heat divided by moles times degrees Celsius. Probably the most common form of heat capacities that we'll use, though, are called specific heat capacities. The word specific here has a technical meaning. If you see specific in a heat capacity, or a heat capacity denoted with a lowercase c, this always means the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. And again, it only applies to pure substances. And since it's the most common, I want to take a little bit more time to look at the form of the specific heat. So we know it has units of joules per gram Kelvin by the definition, and that's the same thing in this case as joules per gram degree Celsius. Here's an equation for the specific heat. It's the heat per unit mass per temperature change. So joules per gram Kelvin, or joules per gram degree Celsius. And it's worth thinking about this just a little bit. Whenever you calculate a change in temperature, you can use either degrees Celsius or Kelvin interchangeably. They give you exactly the same thing. The point of this is that the Kelvin scale, the units on the Kelvin scale, are exactly the same size as the units on the degrees Celsius scale. It just starts at a different 0. But when you take a difference, the difference you get is going to be identical. In fact, let me just show you a very, very quick example of this. All right, suppose we have a temperature change from 19.8 degrees Celsius to 24.8, and we calculated delta T. Delta T, of course, we always take the final temperature minus the initial temperature, and we get a temperature difference of 5.0 degrees Celsius. What if you insisted on converting to Kelvin first? That would be a bad idea because they're interchangeable in this case, but if you did, what would happen? Well, you'd add 273.15 to each of these temperatures, all right, to 24.8, 19.8 plus 273.15. You get 297.95 Kelvin minus 292.95 Kelvin, and you would once again get a numerical value, 5.0, that is exactly the same as what we got before. And let me point out exactly why. It's because you've added the same number on both sides of this equation. So the 273.15 that you added cancels out because of the minus sign here. And so it's a waste of time to convert to Kelvin. You can use either unit interchangeably in this case. Now it's worth knowing that water has one of the highest known specific heats. And this is useful to know both because we use water all the time, it's a useful number to know, and it's also useful to put into perspective specific heats for other substances. Okay, so once I tell you water is one of the very highest known, and I tell you that it's 4.184 joules per gram Kelvin, you should recognize that number, by the way, because that comes from our old definition of the calorie that we introduced at the start of this chapter. Remember, 1 calorie is 4.184 joules, but a calorie was defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius, literally a specific heat definition. In any case, once you know that the specific heat of water is 4.18, you should expect specific heats for any other substance to be smaller than that. So that if you did a calculation and came up with a specific heat of something of 12.8, you would know you have a wrong answer. You should go looking for where you made your mistake. So let's look at an example of applying the idea of specific heat in a calorimetry type calculation. This calculation is a little bit on the complicated side, but let's walk our way through it. So suppose we take a 30.00 gram block of pure aluminum and I put it into 50 grams of water initially at 20 degrees Celsius in a calorimeter that prevents heat loss. So I've got hot aluminum, I'm putting it in cool water. The combination is going to reach a final temperature so that both the aluminum and the water will be at the same final temperature, and that's found to be 20.5 degrees Celsius. The question is, what was the initial temperature of the aluminum? All right, at first blush, this might seem a little bit overwhelming. There's so many pieces of this puzzle. There's masses, there's temperatures, there's temperature changes, there's specific heats. How do you put it together? Well, take your time and think about first principles. The first fundamental principle, the most important part of this whole calculation, is the application of the first law of thermodynamics, which says that the heat lost by the hot aluminum has to equal the heat gained by the water. Why? Because we can't destroy or create energy. If one substance loses heat, it's got to go somewhere, and if the calorimeter prevents it from escaping into the surroundings, it must go into the water. So we can write that algebraically as, remember, Q is always heat going into something, so minus Q, aluminum, that's the heat coming out of the aluminum, is equal to the heat going into the water. Once you have that first equation, now it suddenly becomes a little bit easier to set up this problem because these Q's, these heats, are related to specific heats through the definition that we just looked at. So we can calculate the heat gained by the water just by applying the definition of specific heat. We know from the definition that the heat is equal to the specific heat of water times the mass of water times the temperature change of the water. And in this problem, we know all of these numbers. We know the specific heat of water. I just had it on the previous slide. It's also in this table to fewer significant figures. We know the mass of the water because that's given in the problem. We know the temperature change of the water. That's just the final temperature minus the initial temperature. And so we can calculate the amount of heat gained by the water. Now let me just point out carefully here that since we only know the temperature change to two significant figures, we really only know this number to two significant figures. But as in all cases, we're going to round at the very end of the problem to avoid round-off error. So just keep in mind, we only know that number to two significant figures. All right, we now know the heat gained by the water. We also can calculate the heat gained, notice I'm using heat gained, by the aluminum using the same definition of specific heat. Notice this equation is practically identical to this one, only it's for aluminum. Heat capacity of aluminum, mass of aluminum, temperature change of aluminum in all cases. It's the same equation, just applied to aluminum. It's just that in this case, we don't know the temperature change of the aluminum. That's okay, we can solve for it. And in fact, I can set this up by putting in the specific heat of aluminum, which I get from table 5.2, read off aluminum, 0.90 joules per gram Kelvin. I know the mass of the aluminum from the problem. I know in principle that the temperature change is the final temperature minus the initial temperature, and it's the initial temperature that we want to solve for. So solving this partially, now notice that I've used the fact that Q aluminum is minus 104.6. Where'd the minus sign come from? It came from this equation, right? The heat lost by the aluminum is equal to the heat gained by the water. The heat gained by the water is 104.6. Therefore, the heat lost by the aluminum minus Q is 104.6. Therefore, Q, not minus Q, is minus 104.6. Set that equal to this. This 27 is just the 0.9 times the 30. And then solve for the initial temperature, and I'll leave the rest of the algebra to you, but you should be able to get that the initial temperature was 24.4 degrees Celsius. Now let's look at what calorimeters actually look like. We have two types of calorimeters. Bomb calorimeters. A bomb calorimeter specifically refers to a calorimeter at constant volume. Remember, we said that at constant volume, the heat measured is literally the change in energy, not the change in enthalpy. To do this, we must use a rigid container that prevents any volume change, and that's referred to as the bomb, and that's this very rigid container down here. It's typically made out of very solid, thick steel walls that prevent any change in volume. And a commercial version of a bomb calorimeter looks something like this. This is a calorimeter made by the PAR calorimeter company. This item here is the bomb. It's very, very heavy-duty stainless steel. It gets lowered down into this container here, which holds the water, which is where we measure a temperature change. A constant pressure calorimeter, commonly referred to as a solution calorimeter, in this case, the heat measured is the change in enthalpy. And here's a schematic of a laboratory constant pressure calorimeter. We have a jacket down here to prevent heat loss, a container for water, an insulated cap through which we pass a thermometer and a stirring device. Here's a little bit more complicated equivalent of a commercial device where we have stirring and a more precise thermometer, a jacket to prevent heat loss, and this is what it looks like. In principle, this is a PAR calorimeter, again, a solution calorimeter. Now, in contrast, the calorimeters that we use in our laboratory for chemistry 171L, where you are going to be measuring a heat, are a little bit less complicated. We used to use a coffee cup calorimeter, which is just nested styrofoam cups. We now use this. This is actually a photo of the equipment that we use in our lab. It's a styrofoam jacket into which we put a 250 milliliter beaker, and then we have an insulated styrofoam cap through which, in these two holes, you can pass a thermometer and a stirring device, and we can use that to measure solution temperature changes, and you'll be doing that in one of the labs in our lab section.